When the Atmos plane was added, the first thing that we noticed was that spheres looked oblong when viewed through the refraction. The only way to overcome this was to make the spheres as flat as possible. For the moon, it could not be perfectly flat, or the phases would not work. So the moon is a very flat sphere, or almost flat, but not 100%.
Run.
Of course it's serious. This is capital letters B-I-G, as in Galileo. Time to rethink geocentrism.
The only way to overcome this was to make the spheres as flat as possible.
Allow me to now share the information that will close the case forever on the possibility or the falsity of the moon being a sphere. The moon is 100% absolutely not spherical, and any lunar eclipse proves it, and you can prove it too. All you need is a light source and two spheres. On the right, I'll be showing video footage of past lunar eclipses that we are all familiar with. And on the left, I will be showing what a shadow moving over a sphere actually looks like. A lunar eclipse is not, I repeat, is not a shadow of a sphere or anything else circular moving across a spherical object. How do I know? There are 4 critical points of observation everyone should be looking at, and I like to call these the conformation to surface factor, the shadow diffusion factor, the sine wave or S factor, and the reflected light factor. Firstly, I would like to point out the consistency of how a shadow naturally moves along varied surface types. This is the conformation factor. A shadow will conform to any shape that the surface takes, thus, in a way, revealing the true shape of an object. If a shadow moves along something rigid like stairs, it will take the stairs' shape, revealing the level differential from step to step. If a shadow moves along a concave object like a bowl, the shadow will stretch and skew, revealing the concavity of the bowl. If a shadow was to move over the surface of a sphere, it would stretch and skew in a spherical manner, wrapping and receding as it bevels and distorts along the sphere's surface. Note that this does not and has never happened on the surface of the moon during an eclipse. Which brings us to our next factor, the shadow diffusion factor. Note, the shadow is more crisp on the edge of the bowl than it is in the lowest portion of the bowl, and sharpens as it rises back up to the edge or the source of the shadow. Note also that on a sphere, the shadow is most diffused or scattered around the edges as the sphere's surface recedes, and it is the most sharp or defined on the closest portion of the sphere. This is because the closer the source of the shadow is to the surface, the more defined its edges. The further the source of the shadow is from the surface, the larger and more faded or diffused it becomes. Another way to say this is if you place an object on a surface with a light source above, the object's shadow will appear most sharp when the object is at rest. But lift the object closer to its light source, and you will see the shadow lose its crisp edges and dull or fade away, sometimes to the point where little to no shadow remains. This is the shadow diffusion factor, and in conjunction with the first factor, the conformation to the surface factor, the shadow not only rises and falls, stretches and skews with the surface, but also sharpens and dulls. These 2 factors are almost all we need to find the true topography or shape of the moon. Yet one factor is missing. This is called the sine wave factor or S factor. Because the moon is said to be a sphere, the shadow that is projected onto the moon should also take on the characteristics of the sphere. This critical factor does not appear on the moon's eclipses whatsoever. The sine wave factor, or the S factor, is what happens as an object, round or straight, spherical or bent, passes over a sphere's surface. As the shadow moves onto a sphere, it is wrapping around its curve. Starting from the outer edge and moving towards the middle, the shadow takes on the spherical contour and bends upward at its height, then falls backwards in a barrel-distorted manner. The shadow will always follow the closest edge due to perspective. The shadow will continue to create the S shape until it reaches the halfway point. As the shadow moves beyond the halfway point, it begins to bevel outward again in a barrel distortion manner. When a shadow moves along a 3D sphere, the center or closest part of the sphere to the observer is the most flat, and the shadow's shape and size the most true to life. The sphere will never be flat, but the bigger the sphere is, the less acute the angle of its curvature. So, because the innermost portion of the sphere is the closest to the observer, the less curvature is observed. However, when we observe any lunar eclipse, there is no wrapping, stretching, skewing, sharpening, or dulling of the shadow. In fact, every single lunar eclipse looks as if there is one flat disk moving across another flat disk. As the circular shadow moves along the moon, it maintains its circular shape the whole way at the same pace. No stretching, no skewing, no sharpening or dulling. Anybody can do it. Just go outside and look up. And in case you're wondering about what Neil deGrasse Tyson has to say on the matter, just look how he debunked himself. He went on social media, yes, supposedly the world's leading astrophysicist, anyway, went on social media and posted this ridiculous photo of what he thinks the shadow of a flat Earth would look like on the moon. Now, of course, he believes that the moon is a sphere, or at least that's what he says. But if that's the case, then why is there no stretching or skewing of this shadow? Once again, it goes to show you how important it is to be observant and to rely on your own senses. It also displays the innate sense for acute observation to a true artist.